Good evening, everyone. Welcome back to our faculty development program on artificial intelligence and machine learning. So we'll quickly recap what we have covered in the last day and we'll start with a new topic. It is KNN. Right. So we started with a project management methodology called Crisp-MLQ. Crisp-MLQ stands for Cross-Industry Standard Process for Machine Learning with Quality Assurance. Right. So under Crisp-MLQ, we have 6 phases. Right. So what are these 6 phases? The 6 phases that we have are business and data understanding, then data preparation, right? Then the third phase under Crisp-MLQ is model building. We'll build a model. And the model that we have built should be evaluated. Evaluation. Next to evaluation, we'll deploy the model. Deployment. And finally, monitoring and maintenance. So these are the 6 steps that we have, the 6 phases under Crisp-MLQ. Business and data understanding, where we understand the business and the data, okay, of our client. Business is nothing but understanding the business problem, guys. Post understanding the business problem and the data, we will perform data preparation. Under data preparation, again, we have 3 subphases. What are they? EDA, data pre-processing, also called as data cleaning, and the third one is feature engineering. It is feature engineering. So we have learned EDA topics. Yes, under EDA we understood first moment, second moment, third moment, and fourth moment. Apart from these 4 moments, we also understood graphical representation. What does first moment capture? The center value, the representative value. Second moment captures the spread from the center, the deviation from the center. Third moment, it captures the direction of spread. Towards which direction do we have the long tail is what third moment captures. Fourth moment, business decision, it captures the peakedness. Whether we have a long tail or wide tail, we long peak. Okay, so either we have a long peak or sharp peak. If not a wide peak, we'll understand as part of fourth moment, and we will also visualize the data. Under graphical representation, we have univariate visualizations and bivariate visualizations. Am I right? Yes. Under univariate, we have understood histogram, box plot, QQ plot. Under bivariate, we understood scatter plot. What is the purpose of scatter plot? Scatter plot helps us to understand the relation between 2 variables, 2 features, 2 columns. Then histogram helps us to understand the data distribution. Box plot helps us to understand the presence of outliers. Whether outliers are present or not, we can understand from box plot, guys. Right. Then next to box plot, we also understood QQ plot. quantile plot. Okay, so what exactly does this quantile plot tell us is, it helps us to visualize whether the data is normally distributed or not. And finally, scatter plot, which helps us to understand the relation between two columns. So these are the topics that we have learned under EDA. And in the last session, we understood data cleaning steps. How many steps did we discuss under data cleansing? What are the different steps that we discussed under data cleansing? There are in total 9 steps. Data cleansing is also called as data pre-processing. It is also called as data pre-processing. Also called as data wrangling. And few people name it as data munging. Okay. So these are the different names given for data cleaning. Okay. Under data cleaning, there are 9 steps. So what are the 9 steps, guys? Typecasting. What is typecasting? What is typecasting? Typecasting is nothing but, conversion of data type from one type to other type, that is exactly called as typecasting. Then the second one is handling duplicates. So if we have duplicates in the data, we are supposed to remove these duplicates. We use duplicated and drop underscore duplicates function. Duplicated for identifying and drop underscore duplicates for removing these duplicates from the data. Third step, outlier treatment. Outlier treatment, where we treat the outliers. Which technique did we understood? Winsorization. We have understood winsorization? Yes. So as part of winsorization, we are able to treat the outliers. Then next to outlier treatment, we discussed zero and near zero variance. We calculate variance? Yes. So in general, variance represents the average spread from the center. So we calculate the variance for the columns, and if we found that any of these columns have zero and near zero variance, such kind of columns to be eliminated. They have to be removed because they doesn't work for any kind of analysis. Next to zero and near zero variance, did we discuss discretization? What is this discretization, guys? Discretization is a process in which we convert continuous data to discrete data. We also name it as binning. If we are able to do it into 2 bins, it is called binning, binarization. Okay. If you are going to convert the continuous data into more than 2 bins, it is called discretization. Okay. Next to discretization, we understood feature encoding or dummy columns. What is this feature encoding or dummy column creation? Is when we have non-numeric columns, and if you want to convert these non-numeric columns to numeric columns, we perform dummy variables creation or feature encoding step. Is this step mandatory? Yes. If it is mandatory in the case of, if you find any of the non-numeric column, okay, which is important with respect to the use case, then this step has to be done. So whatever columns you are trying to convert has to be mapped with your business case, the business problem. Only then you are supposed to perform feature encoding. Not all non-numeric columns should be converted. No, not required. There will be only a few columns that are relevant and such kind of columns to be encoded. Then next to feature encoding, did we discuss handling duplicate missing values? Handling missing values. So if we have missing values, we'll perform imputation. And different strategies that we have used are mean, median, mode, and constant imputation. When do we use mean imputation? When there are no outliers. If I don't have outliers in the column, I'll go with the mean imputation, guys. If I have outliers, we'll go with the median imputation. Okay. If I'm working on a non-numeric column and if I want to perform imputation, I'll go with the mode imputation. Okay. So in this way, I'll perform imputation to handle the missing values. Next to handling missing values, we discuss transformations. Transformations is a technique which helps us to convert non-normal data to normal data. If I have non-normal data, this non-normal data will be converted to normally distributed data. So that is the purpose of transformations. We have manual transformations like log transformation, exponential transformation, square transformation, cube transformation, square root, cube root, reciprocal, so on. There are multiple transformation techniques. But there is also an automated technique called box Cox. We understood, right? Box Cox works well for the data which contains only positive values. If the data contains negative values, box Cox doesn't fit on it. No. And finally, we also understood feature scaling or feature shrinking. It is a technique in which the features get scaled to a particular range. What are the techniques that we have understood under feature scaling? Standardization, normalization, and robust scaling. Standardization uses the formula x minus mu by sigma. X minus mu by sigma, where mu represents mean. Sigma represents standard deviation. Right? So this formula will be used by standardization, which returns, mean for all the columns as 0 and standard deviation as 1 for all the columns post applying standardization. Okay. Then as part of normalization, it uses the formula x minus min by max minus min. Okay. So the minimum value and the maximum value. X represents the data. Okay. So when we use this formula for normalization, what happens? The output of normalization will be minimum value for all the columns will be 0 and the maximum value for all the columns will be 1. This is the output for normalization. And finally, robust scaling, which uses the formula, x minus median by IQR. When do we use robust scaling technique? When we have outliers in the data. When we have outliers in the data, we go with robust scaling technique. And the output of robust scaling will be median for all the columns will be 0 and IQR for all the columns will be 1. So these are the important topics that we have discussed as part of data cleaning. And guys, if you have gone through the previous sessions, for sure you can take any structured data, any data set, and you can perform EDA data cleaning. Job done. Because we have understood all the topics related to, the basic data analysis, data visualization, and data pre-processing steps. And today, in today's class, we are going to understand model building part. So, as part of phase 3, we will build a model. But what is a model? What did we understand earlier? Model is nothing but a mathematical equation. Am I right? That is what we have understood. Model represents a mathematical equation. This mathematical equation is what we are trying to build. But how can I build? I just had only data with me. I just had only historical data. It is not data, it is historical data. What do you mean by historical data? Historical data is the data that we have till yesterday. I'll come up with this particular topic again, guys. I'll take an example and I'll explain you. Okay, so we just had only the data that was shared by the client. By taking this data, how can I build an equation? Might be your question, right? So here the concepts of machine learning and deep learning comes into the picture. We use the concepts of machine learning and deep learning. So the algorithms under machine learning and deep learning will be used. As we are running out of time, we have decided to come up with the widely used algorithms in real time. Simplest algorithms and widely used. One such algorithm is called KNN, which means K nearest neighbors, which means K nearest neighbors. So this is one of the algorithm under machine learning, which is widely used in real time. And this is very simple to understand. Implementation is very simple. Okay, so as part of today's session, we are going to understand the concept of KNN. What is KNN? Okay, how KNN works. Then implementing KNN on a use case. We'll take a use case and on that use case, we are trying to use KNN. This is what we are going to do. I hope the agenda is clear. Now, let me, as usual, start with explaining the machine learning primer. Because under machine learning, we have machine learning is broadly classified into 3 types. Can any one of you tell me what are the 3 types that we have under machine learning? Any idea? Machine learning is broadly classified into 3 types. The first one is called unsupervised learning. Unsupervised learning. The second one is called supervised learning. And the third one is reinforcement learning. Reinforcement learning. And you know, out of these 3 types under machine learning, the widely used type of machine learning is supervised learning. So all these 3 different types of machine learning will have algorithms. Okay, so let us understand the difference between the 3 types. First of all, unsupervised learning. When do we generally use unsupervised algorithms? Are when we have unlabeled data with us. When we have unlabeled data. Hold on, what is unlabeled? Unlabeled data is the data in which there is no output column. I should better keep it in this way. Y is absent. What is Y? Y represents output. X represents inputs. Okay. Then next to unsupervised, we have supervised learning. When do we generally use supervised learning algorithms? When we have labeled data with us. When we are working on labeled data, we use supervised algorithms. So that means Y is present. Within the data, if I have output column, then we use supervised learning algorithms. Then what about reinforcement learning? It is not about labeled data or unlabeled data. The model gets trained based on its rewards. Okay, so this is completely a different set that we have under machine learning. If I just compare only supervised and unsupervised learning, okay, unsupervised learning algorithms are used on unlabeled data where it returns us the patterns. What is the purpose of building an unsupervised model is to extract patterns from the data, to extract insights from the data. Okay, and widely used algorithms under unsupervised learning are clustering examples. Clustering is one of the widely used algorithm under unsupervised learning. What is clustering? Clustering is nothing but making your data into groups. We'll group the data. We'll perform segmentation. This is very, very, very widely used in real time. All of you might be part of this clustering activity. Without you getting noticed on your data, somehow any of the retail industry, okay, any of the even a banking sector might perform clustering activity on your data. You might not be noticed because you'll give your data. When you provide your data, what the third, these retail stores or the banking companies, what they do is they'll do customer segmentation. They'll do customer segmentation. I'll just give an example, guys. See, if you walk in to a retail store, a physical retail store, like where we have D-Marts or Ratnadeeps, Walmart, so on, right? So probably they'll ask you for your basic details in some of the stores. Yes, when you provide these details of yours, what they do is in the back end, they'll try to analyze your data and they'll understand your performance. Okay, they'll understand your patterns and they'll perform customer segmentation. You will be made into some groups. Which customers are, purchasing more? Which customers are purchasing moderately? Or the customers which are purchasing very low. So in this way, they can perform segments, groups. That is how, clustering algorithm helps them to perform the task. Clustering is one of the widely used algorithm under unsupervised learning. Then next to clustering, we have dimensionality reduction. Dimensionality reduction. So the name itself is telling it is going to help us to reduce the dimension of the data. When we use the algorithms under dimensionality reduction techniques, the dimension of the data gets reduced. Okay, so that means under clustering or dimensionality reduction techniques, whatever we are going to use, the algorithms they work on unlabeled data, which means Y is not present, Y is absent. And what is the purpose of unsupervised learning algorithms is they help us to extract the patterns, the insights, the hidden insights from the data. Coming to supervised learning. What is the purpose of supervised learning algorithms is they help us to work on labeled data. What is labeled data? Labeled data is nothing but the data in which we have Y column, output column. And when we use supervised learning algorithms, we can predict the new data. We can predict on the new data. How? We have output, right? When you have output, we'll train the model in such a way to predict the future. Okay, so that is how we are able to predict temperature. Okay, we are able to predict which team will win. Okay, in real time, supervised learning algorithms are widely used, guys. Compared to unsupervised learning, supervised learning algorithms are widely used. Predictions can be done. Examples, we have classification algorithms and we have regression algorithms. We have classification algorithms and regression algorithms. So supervised is again of two types. The first one is classification and the second one is regression. When do we use classification algorithms and when do we use regression algorithms is when the values present in this Y column are discrete. What do you mean by discrete? Discrete means fixed. Discrete means fixed. So if the values under the Y column are fixed, output column, under the output column, if they are fixed, we use classification algorithms. Examples, naives, KNN, decision tree. So these are called shallow methods, shallow techniques, which are widely used for classification. Apart from classification, we can also use these algorithms for regression. Now let me come to regression. When do we use regression algorithms? Regression algorithms are used when the values under the Y column are continuous. If the values under the Y column are discrete, we go with classification algorithms. If they are continuous, we go with regression algorithms. Examples, linear regression. Okay, linear regression is one of the widely used regression algorithm. We have logistic regression. Okay, so on. I'll come back. I'll repeat it once again. Supervised algorithms are of two types, classification and regression. On what basis they were divided? They were divided based on the values that we have under the Y column. If I give an example, probably that will be clear, right? So I'll give an example. If I have a use case to predict whether a person have cancer or no cancer, a patient walking into the hospital, I am supposed to predict whether a patient have cancer or not. So what values do you see here? They are discrete, fixed values. So it is a problem of classification. They are discrete. Can I have anything else in the output? No. Either I should say whether the patient have cancer or not. I represents the model, guys. The model should predict whether the patient have cancer or not, disease or not. So here the values are fixed. When the values are fixed, which kind of algorithm should be used? Classification algorithms. Coming to regression, if I have built a model and this model has to predict the price of a house, okay, or if I want to predict the price of a stock, stock price prediction is an example of regression. Because will the stock's price be fixed? No, they will be continuous. They are continuous. As they are continuous, I am supposed to use, regression algorithms. House price prediction. House price. Based on some XYZ factors, I'll be predicting house price. The location, the number of bedrooms, or we have the square feet. Okay, either it is east facing, west facing. I'll take all these conditions in the picture and I'll build a model which helps us to predict the house price. House price, will it be discrete? No, it is continuous data. Then, so there we use regression algorithms. I hope it is making sense. So today we are going to learn one of the widely used algorithm of shallow technique. It is KNN, K nearest neighbors. Okay. So before we start understanding about KNN, what exactly is KNN and how KNN works, we'll discuss about ML primer because this is mandatory. Because if you understand what exactly is ML primer, if you understand the concept of ML primer, the same flow will be used for all the rest of the supervised algorithms. The same flow will be used for all. I'm just mentioning it for all supervised algorithms, guys. Not just for one, for all the algorithms. So focus on this primer. Very, very important. The same flow will be used. If you get any questions, just make a note of them. I'll be addressing your questions at the last. Right? Yes. So first of all, let us understand ML primer, machine learning primer. So what client is going to share us? The client will share us data. And this data is called historical data. This data is called historical data. The data that we have till yesterday, the data that we have collected till yesterday is called historical data, past data, right? So this historical data, what I'll do is, I'll make it into two parts. I'll make it into two parts. What are these two parts? These two parts are called train data and test data. Train data and test data. I repeat, the historical data that we have will be made into two parts. One is train data and the other one is test data. But whenever you are splitting your data into two parts, train and test, always remember this point. Train data should always be greater than test data in size. Train data should always be big in size compared to test data. Right. Now, what is the purpose of train data is, on the train data, I'll build my model. I'll use the model. I'll build this equation, the model, using the train data. Using this train data that we have, I'll build this model. And once after building the model, once after training the model, I'll take it and I'll use it on my test data. Once after building the model, I'll go and test it on the test data. So what I'll get? This, when I use it, I'll get predictions. I'll get predictions. So these predictions we represent with y cap. We represent with y cap. As we have predictions, we also have actual data, right? So we'll compare actual with predictions. When you compare the actual output with the predictions, okay, you will calculate accuracy. And this accuracy is called test accuracy. Why? Because you are doing this process on test data. I'll do the same on the same thing. I'll do it on train data. When I do it on the train data, again I'll get predictions, but these predictions are related to my train data. I also have the actual. Yes, actual will be compared with the predictions so that you'll get train accuracy. You'll get train accuracy. So guys, if you don't understand it, I'll repeat it with an example. I'll take an example. Now I'll repeat the same. Assume I have a project in my hand. Okay. I had a client with me and the client shared a data and the data is of size 100 by 5. 100 by 5. The size of the data is 100 by 5. What are these 100 by 5? 100 represents rows. 100 represents rows. 5 represents columns. 5 represents columns. Now, let us understand. If I say 5 columns, that means out of 5, 4 are inputs, obviously. Because this ML primer that you are seeing here is only for supervised algorithms. So when I say supervised, obviously you will have output. So 4 will be inputs and 1 will be output. 4 columns will be inputs and 1 column will be output. Okay. Now, taking this 100 by 5 in which we have 4 inputs and 1 output column, what is the first step? To split the data into 2 parts. What are they? Train data, test data. Okay. So on the train data, we know that there is a condition. There is a rule that train data should always be greater than test data. Okay. I kept the train data percent as 70%. What will be the size of test data then? 30%? Obviously, 70 plus 30 will be 100. 70 plus 30 will be 100. Now, if I say 70%, can you tell me the dimension for train data? What will be the dimension for train data? %70%, right? So obviously the size will be 70 by 5. Out of 100 records, you have 70% you are giving it for train data. So that means your train data size will be 70 by 5. So test data size will be 30 by 5. Yes. 70-30 guys, proportions. Now, 70 by 5 represents the train data. Can you tell me the size of inputs in train data? Tell me the dimension for input data that we have under train data. It will be 70 by 4 inputs. And for output, 70 by 1. This is output. In the same way, 30 by 4, 30 by 1. I hope you are getting the point. Right? So, in order to train that model, in order to train this equation, we'll pass this entire data. We'll pass the entire data, both inputs and the output will be passed so that the model starts learning the patterns. The model starts learning the patterns. Once after the model get trained, we'll use it on the test data where we pass only inputs. Only inputs will be passed. When you pass only inputs, you'll get predictions. When you only pass inputs to this model, you'll get Y cap. You'll get Y cap. Y cap is nothing but predictions on the test data. But you also have actual. I also have actual. So I take this actual output, Y. I have predictions. Let me compare. Whether my model is giving right predictions or not, I'll compare. When I compare, I'll get accuracy. I'll get accuracy. Since I'm doing it on the test data, this is called test accuracy. This is called test accuracy. I'll repeat the same process on the train data. I'll repeat the same process on the train data where I'll get train accuracy. And these accuracies that we get, train accuracy and test accuracy, should be close to each other. They should be close to each other. They cannot be very far. We cannot have very big values. Values in the sense, say if I get 90% for train accuracy, and if you say for test accuracy, it is only 60%. That doesn't mean any sense. Because we can clearly understand the model is not performing on the new data. Right? So the difference between train and test should be maximum 5%. 5 is industry standard. Okay, such kind of model is called right fit model. Such kind of model is called right fit model. What is a right fit model? A right fit model is a model which returns good results on both the train data and the test data. Which returns the good results. I'm talking about accuracy. So accuracy means how accurate your results are on the train data. So a right fit model will give us high accuracy on train data and high accuracy on test data. Such kind of model is called right fit model. The accuracy will be very high. And we also have underfit model. Underfit. Underfit is again a model which does not perform on train data itself. Okay, the model was built using the train data. It got trained using train data. Yes. If I check with the train accuracy, if the accuracy of the train is very less, then such kind of models are called underfit models. Such kind of models are called underfit models. We have third fit as well, overfit. What does overfit model talk about? Overfit models talk about the models which perform well on train data. So the accuracy will be very high on the train data, but coming to the test data, the accuracy will be very low. That is called overfit models. So in general, you cannot directly expect a model which is right fit. No, you do lot of experiments. We do lot of experiments. When we do lot of experiments, we'll get a right fit model. Okay, we may get underfit models and overfit models initially, but we'll tune the model to become the right fit. What does right fit means? A model which performs very well on both train and test data. So why it should perform well is, if it is capable of performing on the data which got trained, it should also perform well on the unseen data. Only then we can say it as right fit. Because if I use this model post training, see, post completing this, if I evaluate it and if it is giving good results, obviously this model should perform well on the new data. This is historical data, right? On the new data, see, if I'm running a business, okay, probably the data will be generated on daily business. On daily basis, the data will be generated. So this model that we have built should also perform well on the new data. If it is not performing well on the new data, what is the use case? There is no use of building the model, deploying, right? So that is why we are interested in getting the right fit model. We'll build the model, we'll evaluate it. Only if it is right fit, then we will deploy it. This is what we do. I hope it is clear with respect to the fits and the ML primer. Whatever we have discussed here, you'll observe the same when we are trying to implement the logic using Python. Okay, when we use the concept of KNN, I'll use the algorithm KNN to build the model. Okay, so you'll observe the same steps, taking the data, performing EDA, then followed by data cleaning. Once after completing data cleaning, we'll start from here, splitting the data, where splitting should be done in a way like train data should be more than test data. That means every time it should be 70-30? No, it can be 80-20 also. The condition should be satisfied. Okay, so post splitting, we use train data, both inputs and output to train the model. Once after the model got trained, we'll calculate the accuracies. How? We pass only the inputs of the test data, we'll get the predictions on the test data, we'll compare the predictions of the test data with the actual of the test data, where we get the test accuracy. This text accuracy will be documented, will be reported. Apart from it, the same process will be done on the train data to get train accuracy. Once after having both the accuracies, we will compare. If they are close to each other, then we can say that we got a right fit model. Making sense? Now, let us start the algorithm KNN. Because so far we just understood what exactly happens for each and every, unsupervised learning algorithm. Okay. Now let us understand what exactly is KNN. KNN stands for K nearest neighbors. KNN stands for K nearest neighbor, and it is one of the simplest algorithms, guys. In the entire machine learning, KNN is one of the simplest algorithm. It is called as non-parametric algorithm. Why it is called as non-parametric algorithm, we'll discuss. Which we use KNN for both the task, classification and regression task. So in general, KNN is widely used for classification. Then it doesn't mean we cannot use it for regression. We can use it for regression. Okay. But what exactly the logic that KNN uses? It uses the concept of distance. The logic that used by KNN algorithm is distance logic. Okay. So whenever there is a new data point, and if I want to assign the class, see, there are two classes. One is green class and the other one is red class. There are two classes. And if there is a new class, if there is a new data point, and for this data point, if I want to assign to one of the class, I'll use the concept of distance. Accordingly, for the new data point, the class will be assigned. How? We initially get the K value. What is this K value? K value represents neighbors. How many neighbors to be considered? Okay. So if you see here, I'm considering 5. K value as 5. So by calculating the distance for all the data points present in this, plot, from this point to each and every other point, the distance will be calculated and the 5 nearest neighbors will be considered. If you see within the circle, for the new data point, you see 5 nearest neighbors? Yes. Out of these nearest neighbors, okay, so you will go for the majority rule. Do we have green or red? Which class points in majority? It is green. So obviously for the new class, for the new data point, it will be assigned as green. That is how, KNN works. In short, it uses the logic of distance. It uses the logic of distance. Why it is called as lazy learning algorithm? Because to be honest, KNN does not learn anything during training. When you are training the model, it does not learn anything. It stores the data. The training data gets stored for predictions during testing. That is why it is called as lazy learning algorithm. It is also called as non-parametric algorithm. The reason behind it is it does not consider any kind of assumptions. No assumptions. If you take other algorithms, majority of the algorithms will have assumptions about the data distribution. But KNN is a non-parametric algorithm, which means it does not have any assumptions. No assumptions. Whatever the data might be, it uses the logic of distance. Now, let us understand, how exactly KNN works. We have the steps defined one by one. Okay. So this is how KNN works. For regression or classification, initially we define the value for K. The K value, what does K represents? K represents number of neighbors. K represents neighbors. The number of neighbors will be defined upfront. Then, second step is to calculate the distance. The distance from the new point to all the points in the plot, in the visualization, if you see, it calculates the distance for all the other points. From the new point to all the points in the data, the distance will be calculated. And we use distance metrics like Euclidean distance. Did we use Euclidean distance earlier? Yes, probably in our school days, we have used the concept of Euclidean distance. What is the formula for Euclidean? Square root of x1 minus x2 whole square plus y1 minus y2 whole square. Right? So even we use Euclidean distance for calculating these distances. There are other metrics like Manhattan distance, Minkowski distance, then cosine, similarity. There are multiple metrics to calculate the distance. Once after calculating these distances, among the neighbors, we select the k nearest neighbors. We have defined k value, right? So accordingly, we'll come up with the k nearest neighbors. If I say k is equals to 3, what does that mean? The 3 nearest neighbors have to be selected. How we are saying nearest? Nearest neighbors are decided by the value of distance. If the distance is very less between the new point and the other point within the training set, then we say it is the nearest neighbor for the new point. Right? So we'll identify the neighbors for the new point and then we make prediction. If it is a classification algorithm, we go with the majority rule. The majority voting will be done. If it is a regression task, we go with average. If it is a regression task, we'll perform average. Because regression means we are going to predict continuous data. So in order to predict a continuous data, you should obviously go with average of your neighbors. Okay, so that is how predictions will be done. That's it. This is what happens in the backend. So during training, it does not learn anything. That is one point. That is why it is named as lazy learning algorithm. Instead of training, instead of learning the pattern, it stores the data for making the predictions. Okay, so the challenge that you observe during this journey of the working of KNN, what do you find the challenge? The challenge is selecting K value. Everything is fine, but what value should be given for K? Can you decide it? Is the question. So K becomes a hyperparameter here. In KNN, K becomes a hyperparameter. We'll experiment with different values of K. Okay, so we'll understand. I take different values of K during the journey of use case. So the next slide is about selecting K value. How to select K value? What happens What are the different techniques that we have in selecting k value is elbow method. Elbow method is one way of selecting the k value. If you observe, this is elbow plot or scree plot. Okay. So wherever you see that elbow will be chosen as optimal k value. If not, experiment with multiple k values. In general, we do this. We'll experiment with multiple k values. When you experiment with multiple k values, you'll get at some point of time with some k value, you'll get the best results. Okay, so that results we have to analyze and we are going to take the value of k. But can we take a small k value like k is equals to 1? If I take k is equals to 1, like small k values, I can observe the models have high variance. Overfitting is possible. What if I take a large value for k? There are chances that model gets, the model that we are trying to build will become an underfitting model, high bias. So we have to come up with optimal k value, which balances both bias and variance. In short, we have to identify a k value which returns us the right fit model, and this we achieve via experimenting. We experiment, we'll get the results. The optimal k value will be captured. I have a small example here. There is a small example and you guys have to, answer the questions. So small use case. This is not the actual use case, but trying to understand KNN with a small data set of size 6 and 4. First of all, tell me, is it a classification problem or regression problem? How do you decide it? Based on the Y column. What is the Y column that we have here? Grade category. Grade category. So we have student ID probably x1, input 1, input 2, input 3. What does input 2 says? X2 talks about the number of hours the student studied. X3 talks about the number of assignments the student completed. So in this way, we have 3 inputs and 1 output. It's a classification problem. I can clearly understand. Then, fine. I am clear that it's a classification problem. Then comes the second question. How many classes do we have in this use case? How many classes do we have? It is a 3-class problem. We say it as 3-class problem. How? Identify the distinct categories. If you see here, good, average and poor are the categories that are repeated. So there are 3 classes. Good is a class, average is a class and poor is a class. So that means it is a 3-class problem. Right? So if I have only 2 classes, assume in my Y column, if I have values like S, no, it becomes a 2-class problem. Right? So this is a 3-class problem. Done. Now, there is a new data point, guys. There is a new data point. A new student have probably, joined the class. So we have the data of this new student who studies for 6 hours and this guy has completed 4 assignments. 6 hours of study and completes 4 assignments. And we are supposed to we are supposed to predict the grade category using KNN algorithm. So let us solve it. What is the first step? First step is selecting k value. Selecting k value. Yes. If you see here, so these two are the classes related to poor. These two data points belong to poor. What about the blue one? They belong to average class, and the green one represents good class. This is the new point. This is the new student that we haven't added into the class. Now, let me start taking the distance. Take the distance. If you see k is equals to, if I select k is equals to 3, that means 3 neighbors, 3 nearest neighbors. I'll start taking the distance from the new point to all the data points within the data set. Okay, so if I start taking the distance, x1 is 6 and x2 is 4. So one by one, if I start 6 minus 4 or 10 minus 6, it is 4. 4 square, 16. Probably I'll keep the distance here with 1. The distance is square root of 16 plus 16. It is nothing but square root of 32. Square root of 32, which is nothing but, 4 root 2. Yes. Then in the same way, I'll calculate the distance with the second student from the new student to the second student. What it is? 7 minus 6, it is 1 square, 1. 4 minus 6, minus 2 square, 4. So 1 plus 4, this will be square root of 5. Square root of 5. Coming to the third student, 6 minus 4, it is 2 square, 4 plus 4 minus 3, it is again 1. So square root of 5. Square root of 5. So that means with 2 and 3, the distance is same. Then let me do the same with student 4. Okay. So if I do the same with student 4, what I'll get? 8 minus 6 whole square, it is 2 square, 4 plus 7 minus 4, it is 3. 3 square is 9. This is square root of 13. Then with student 5, 6 minus 6, 0. Then 5 minus 4, it is 1. 1 square is 1. So it is square root of 1, which means 1. Which means 1. And finally with 6. 6 minus 2 is 4. 4 square is 16 plus 4 minus 1 is 1. 3. 3 square is 9. This is 5. 25 square root of 25 is 5. Now, as I took k is equals to 3, identify the three smallest distances, 1, square root of 5 and square root of 5. That means with student 5, with student 2 and student 3 these are the three students. These are the three students who are close to the new student. Now, this is a classification problem, right? So as part of classification, how the predictions are done? Majority. Majority rule comes in. When we say majority, so obviously for the new student, the grade category will be predicted as average. I hope you are getting the point. Yes. Okay. So this is what KNN does. Calculating the distances. If it is a classification problem, for predictions, it uses the majority class. If it is a regression task, it uses the, average of the values. Then Next to the use case, let us talk about the advantages and the limitations of KNN. So coming to the advantages, it is very simple. Okay, easy to understand and implementation is also very easy, guys. Okay, as we understood that KNN is a lazy learning, no training is done actually. It does not train, and it can be used for both classification and regression. Yes, but widely used for classification tasks. We can also use it for regression to predict continuous data. It is a non-parametric algorithm, no assumptions, and it works well for small data sets. What if I have large data sets? Then it is a limitation for us. The reason is, as KNN works on the logic of distance, and if you are working on a large data sets, it becomes computationally expensive. Lot of calculations has to be done. And it is also sensitive to the outliers. If there are outliers, it does not perform well. And one of the no, the most important limitation is the fixing of k value. Choosing the value k will be a hectic task for us. And if I don't perform feature scaling, the results will not be accurate. This point we have already discussed in the last session itself. Okay, so these are a few advantages and limitations of KNN. And finally, let us talk about real world applications. Here are a few applications where KNN can be used. We use it for recognition, facial recognition, handwritten recognition. Okay, then to predict whether a person have disease or not, for recommendation systems, for spam detections. Okay, these are the problems under classification. Text classification. Okay, so if you take a spam detection mail, whether we are detecting a mail as predicting a mail as spam or ham, the classification can be done. As we know that regression can KNN can also be used for regression. The KNN helps us to predict use cases like you know predicting house prices, weather forecasting, temperature prediction, stock market analysis, predicting the price of stocks, churn predictions, and finally crop yield. In case of agriculture, yes, we can also predict the crop yield using KNN algorithm. So these are the applications in case of classification and regression, guys. So out of these, we have took one of the application. Okay. So and we are trying to understand it as part of today's session. So for that, I'll open Spider. We are back to Spider, in which we are going to understand how KNN is implemented. Okay. And for this, we are taking a data set. This is related to, loan, banking sector. So under banking sector, finance. Okay. So this use case is related to banking sector, where we are going to predict whether a person will take loan or not. Okay. So here are the list of columns. One by one we'll understand, guys. So this is actually a classification problem where we are going to classify the personal loan of customers. So we are going to classify the customers in short. And it contains 5,000 customers data. Okay, and there are multiple columns like ID of the customer, customer ID, customer age, customer experience, customer income. Okay, so this is in thousands, and zip code, nothing but the pin code of the customer where they live, and the number of family members. Okay, and the average amount of credit card that is being used by the customer. So like this we have n number of features, guys. Okay, we'll take the CIBIL score. And finally, the personal loan is our Y column. Personal loan is our Y column. What does this personal loan actually tell us is whether the customer accepted the personal loan offered by the bank or not. So this is what our Y column is. So what problem it is? It will be a two case problem. It will be a two class problem. Accepted or not. See, right? So for that we are implementing, we are going to use the KNN algorithm to build a model, and this model help us to predict for the upcoming data. If I launch a similar kind of campaign, see, in general, what banks do is before they launch any event, they'll do as they'll come up with some campaigns. So as part of a campaign, this is what they observe. Okay, so they'll not do it for the entire population. They'll try it on a sample initially. When they do it on a sample, they'll understand whether this particular offer is going to accept by the majority of the customers or not. Right? So I'm going to implement KNN algorithm for which I'm going to import many packages. Okay, so majority of the packages might be new for you guys, but I'll explain from scratch. We know pandas for data manipulation. So I'm going to import pandas as PD. I'm importing pandas as PD. Then next to pandas, what do you see? Pandas profiling. Pandas profiling is an automated EDA package. We have discussed EDA. Am I right? Yes. But EDA that we have discussed is a manual method. Okay, it is a lengthy method. So this automated package called Pandas profiling will help us to automate the entire EDA process. Okay, it helps us to automate the entire EDA. I'm importing Pandas profiling for automating the EDA process. We'll discuss. Then matplotlib.pyplot. Matplotlib.pyplot for visualization. To build a KNN model, we have the function kneighbors classifier. We are importing kneighbors classifiers from sklearn.neighbors. Done. Done. Then next to kneighbors classifier, what are we importing? We are importing classification report, confusion metrics, accuracy score. These are three different metrics which help us to evaluate our model. So I'm importing all the three. Post building the model, they help us to evaluate whether the model is performing well or not, can be understood from the results of these metrics. Then next to the metrics, we are importing a method function called SMOT. So SMOT is a technique which helps us to balance the data. What is the concept of balanced and imbalanced? We'll understand, guys. It is obviously we have to check whether the data is balanced or not. If the data is imbalanced, you cannot build a model on imbalanced data. No, the results will not be accurate. Okay, so that is why we balance the data initially using techniques. Like there are techniques like undersampling, oversampling, okay, k-fold cross validation, then stratified k-fold cross validation, SMOD, so on. So I'm importing SMOD for balancing the data and standard scalar. What is the purpose of standard scalar? The purpose of standard scalar is for feature scaling. In order to scale the features, we are importing standard scalar. Then next to standard scalar, I am importing train test split. So this is a function which helps us to split the data into train and test data. Apart from train test split, I am also importing grid search CV. What does this grid search CV does? Is grid search CV will actually perform hyperparameter tuning. We actually perform hyperparameter tuning. So what is hyperparameter tuning? We'll understand. And finally, joblib for saving the model. For saving the model, I'm importing joblib, guys. Done. Job done. So once after building the model, we are supposed to save it. So that for dumping the model, for saving the model, we use joblib. Okay? Fine. Now, the data is present in an Excel file. Okay. For that reason, I am reading the data from the Excel file using read underscore Excel function from pandas. So the data gets stored in an object df. The data gets stored in object df. If you see here, the data is of size 5000 by 14. 14 columns, 5000 rows. So this is our data. This is our data. Now tell me, do we have any non-numeric columns? No. All of them are numeric. So encoding is required. Encoding is not required because no numeric column. This is my output column. Personal loan, whether the customer accepted or not. Zeros, ones represent accepted or not. That's it. Right. What does head function does? Head function will return the top records. By default, they return 5 records. So if you want to understand the data, you can go through the head function output. But still the problem that you see here is, it is not returning us the entire data. No. It is not return me the entire data. Right. Next to head function, I am using info function. What does info function return? Info function will return me the complete information of the data. See, the data types, the non-null count for each and every column. So do you observe any missing values? No, there are no missing values. So that means we need not work on the missing value step. Handling missing values is not required. We are done. There are no missing values. Now, let me go with the first step, that is EDA. As we know that under EDA, there are, 4 moments and visualization that we are supposed to do. But instead of making my work, not to reduce my work, we have automated libraries, automated packages called like SweetWiz, AutoWiz, Pandas profiling, so on. I'm using Pandas profiling so that this particular package will complete the entire EDA, guys. Within 2 lines of code, you'll observe, right? So within just when we execute these 2 lines of code, this is going to complete the entire EDA. So I'm using profile report function. Okay. So this profile report function will help us to, will take the entire data frame DF and it gives the title name as Pandas profiling report and it initializes the profile report. Done. Now, the results of the EDA, I want the results to be, written to a file. I want to store it in an HTML file. Okay. So let me execute this. It starts working on the data. If you see here in the console, focus all the EDA steps along with the visualizations. You know, you'll get it within just one line of code. That's it. It will take, good amount of time. Observe here, it is actually understanding the data set. Post understanding it, it generates the report structure. See, it started generating the report structure. We are not doing the EDA steps one by one. First movement, second movement, third movement. I'm not calculating. But this EDA, automated EDA package called Pandas profiling will do everything for us. So it will take time. Okay. But it will come up with an HTML file. The results will be reported. Is it done? Yes, it is. See, export report to file. It is done. The report has been created. But how to know that where did I have the report? Where is that report? How should I get the information is, you see here in the top, in this box, this is called current working directory. This is called current working directory. So for me at this location, I will have the report generated. So I'll go back to my system. And if you see here, is this the report which got generated just now? Yes. So double click on it. This report gets opened in a browser. It opens in a browser. Now try to understand the results of Pandas profiling. If you go through this report, you'll understand each and every output. See, it has gone through the data set, right? It identified that the number of variables are 14. Yes, we have 14 columns. Number of rows, 5000. How many of them are missing? 0. No missing values. Missing cells, again 0. So missing cells and their percentage. Duplicate rows and their percentage. So actually we are supposed to do all these steps as part of EDA. Right? But are we doing anything? See, it takes each and every column. The first column is ID. It identifies the unique values, the distinct values, their percentage, missing values, maximum, minimum value. Okay, whether there are any, negative values, zeros, it identifies each and every value, guys, and the plot. If I go to age, you'll observe probably here. How many of the values are distinct under age? Only 45. The distinct value percentage is 0.9. Any missing values? No. Any infinite values? No. The mean value is 45.3. The minimum value is 23 and the maximum value of our customers is 67. Okay, and this is my histogram. How clear it is? See, in this way, I can go through every column. Whatever might be my column, I can go through each and every column. I can understand it to get good exposure with respect to the column data and the visualization as well. So this is actually upon your time. So if you see family, it is considering family as a categorical column in which it identified only four different values, four distinct values, 1, 2, 3 and 4. So Family is actually representing the number of persons in the family of our customer. Okay, so majority of the customers are single. There are only one person in the family. That is what we can interpret. Then credit card usage, average credit card usage per month. And this is the distribution. So in this fashion, it gives for each and every column. Every column. Online, credit card, personal loan. So this is a Y column. Yes. So in the Y column, I can clearly understand, majority of the customers accepted or denied. They denied, but only a few accepted. So I can clearly understand it is a two-class problem, two classes. But is the data balanced? The data is imbalanced. The data is imbalanced. When do you see data is balanced, and how do you see the data is balanced or imbalanced? Very, very important, guys. Balanced versus imbalanced. When do we say data is balanced and when do we say data is imbalanced? We say data is imbalanced when all the classes present in the data, if they don't contain at least 30% of the overall values. I repeat, if all the classes, how many classes we have? There are two classes. 0 is one class, 1 is one class. Accepting, denied. Accepting and denied. So these are the two classes. If you see here, what is the total count of customers? 5,000. What is 30% of 5,000? 30% is 1,500. So each and every class within the data should contain greater than 1,500 records. Only then we say data is balanced. But is that actually working here? No. Not even 10% for one. In case of class 1, it does not contain 10% of the values at least. So this is clearly an imbalanced data. But in case of 0, it is working. But what does this condition say? The definition says all the classes should contain at least 30% of the values. Should contain at least 30% of the overall values. So this is an imbalanced data set. That is why we are using a technique called SMOT. What does SMOT represent is synthetic minority oversampling technique. Synthetic minority oversampling technique. It's an oversampling technique where the minority class will be used to create the synthetic samples. You'll understand, okay? So I can clearly understand this is an imbalanced data set. We'll use techniques like SMOT and we'll make the data set balanced. Before we proceed, again the question comes. So that means every time should we check for the balance or imbalance data? Yes, mandatory. Every time before we build a model, ensure you check for balanced or imbalanced. If the data is imbalanced, you have to make it balanced. What if I don't make it balanced? Your results, your model gets biased to the class which has more values. The class which has highest number of values. So instead of getting the fair results, we have to ensure the data is balanced. If not, the results will not be appropriate. I hope it is making sense. The difference between balanced and imbalanced. Now, we have the plots, the interactions. You can change with the columns so that you'll get the interactions, the plots and all. The correlations you can observe. This is called heat map, guys. This is called heat map. So in the last class, we have discussed scatter plot. Right. The purpose of scatter plot is to understand the relation between two columns. But this heat map will provide the information of the relationship between all the columns. See, ID with all the columns is what you see here. And the color is actually telling the value of small r. You see on the scale, if it is red in color, pure red, it is -1. If it is dark blue, the R value is 1. So obviously the diagonal values will be, the diagonal boxes will contain only blue. But apart from diagonal, I see age and experience are highly correlated. Yes, they are. Even if you see here, experience is the third column, which is highly correlated with age. That is why you see a dark blue color box. So that means R value should be greater than 0.85. That is how we interpret this heat map. This is called heat map. Okay. Then the next plot tells about, this is a count plot which gives the information about the missing values. So none of the column has missing values. And finally a sample data is what it is providing. The first 10 rows and the last 10 rows. So this is the output, the report that was generated by Pandas profiling. The package Pandas profile. Right. So I'll go back and whatever the important insights that I get, I have listed down all the insights that I felt these are important. Okay. So you need not focus on them. I'll directly go to the next step within the code. What are we doing? I'm using drop function. Yes. I'm using drop function to drop the unnecessary columns, the non-relevant columns. I'm dropping the ID of the customer along with the zip code of the customer. Why? Why am I dropping? The reason why am I dropping is these columns are not relevant. How do you say these columns are not relevant with our use case? They are called nominal data. Excuse me. These columns are called nominal columns, nominal data. What does nominal columns mean? Nominal columns mean the columns which written as, which represents an identity. If you take ID column, ID is what? It is giving an identity for the customer. Zip code is an identity for a location. So such kind of nominal columns should be dropped. There is no use of having this nominal columns, nominal data. So I'm dropping these columns. Axis is equals to 1 represents they are columns. In place is equals to 2 represents we are performing in place operation. We are performing in place operation, guys. So within this same object, 2 columns will be dropped. Done. Done. So 14 became 12. Next to it, what am I doing? We found that the experience column of our customers have negative values. It might be a typo error, right? But we are supposed to sort it. Okay. For that reason, I'm going to take the experience values, like the column experience column values, where, the values are less than 0 and I'm getting the count of it. See, there are 3 different values under experience which are negative. -1, -2, -3. Okay. And the count of -1 is 33, -2 is 15, -3 is 4. probably they are instead of -1, it might be 1, 2, 3. Okay, might be it is a typo, guys. So what I'm doing is I'm applying a function called ABS, absolute. So the absolute function will actually does what? It is nothing but the mod. Okay, so -1 will be written as 1, -2 will be written as 2. So in that way, I am applying this absolute function on the experience column of the data frame, and I am storing the results to the same column. Done. I am storing the results to the same column. And finally, I am checking the missing values. We know that there are no missing values. But let me do it. Let me check the missing values. Do you find any missing values in any of the column? No, there are no missing values. Right? So we need not work on handling missing value step. Not required. Then I'm performing feature engineering as a step where I'm including, we have a column called CCAVG, which represents the average monthly credit card spending. The credit card that the customer uses on monthly basis, right? So what is the average amount that the customer is spending from this credit card? We have, but we are supposed to convert it into yearly. The reason behind it is we have rest of the columns like income, which is, where we have documented it for the annual purpose. So in the same way, I'm converting this average monthly credit card spending into yearly basis. So I'll take these values and multiply with 12 so that I'll get the values for yearly basis. Per year, what is the spend? The average credit card spending will be calculated and they will be stored into the same column. Right. Now I'll start splitting the data. Splitting in the sense we are not splitting into train and test case. What am I doing? I'm going to split the data into inputs and output. I'm going to split the data into inputs and output. So if you see inputs, if I just drop personal loan, the Y column from DF, obviously all of them are inputs. So that is the logic I am using here. So I'll use drop function to drop the personal loan column, the Y column, and we are mentioning that axis is equals to 1, which represents personal loan is a column. Okay. So this will drop personal loan column from the data frame DF and the results will be stored to X. What does X represents? The inputs. So obviously 12 minus 1 will be 11. Done? Yes. In the same way, what am I doing to calculate only to get the only output column? I'm taking only the personal loan column from DF. So this will be a series object which contains only one value, one column, the Y column. What it is? Personal loan. So under X we have all inputs, under Y we have only output. Now I'll split the data into two parts. So from here you'll understand the flow of ML primer, guys. You'll understand the flow of ML primer. So what is the first step? The data that we have, we are going to split into two parts, train and test. So I'll use train test split function. Okay. So this function will actually split the data into two parts, train and test, to which I am passing X, Y. What does X means? Inputs. Y means output. And we should also follow that condition, right? What does the condition say? The condition says, The conditions is test size is 30%. Okay. We have already understood that train data should always be greater than test data. Right? Train data should always be greater than test data. So when I say test size is equal to 0.3, that means test size is 30%. Then what about train? Train will be 70%. Okay. Then how you are able to split it is, by default, the train and test data will be split randomly. It splits randomly. So in order to produce the same records every time into train and test, we use a parameter called random underscore state. We use a parameter called random underscore state and we'll provide an integer for it. Okay, it is 42. The reason why we are providing 42 is also let you know, guys. See, what exactly train test split does. Train test split divides the data, splits the data into train and test. Yes. If you see under the train data, okay, if you take train test split, the records, the data that I have, X and Y, inputs and output, will randomly split into train and test. There is no rule. Okay. If I take this data, might be record 1, might be part of train or test. You cannot decide it. Okay. So randomly it splits the data into train and test. Okay. So assume that you have split the data and then you have built the model, everything is perfect. But when you run the same line of code, again it splits the data in randomly. Yes. So when it splits the data randomly, these records might change between train and test. Yes. But which is not accepted. The records that we got initially, they have to sit under the same part, either train or test. So for reproducibility, there is a parameter called random underscore state. Even though if you run this line of code for n number of times, if it initially the record one, if it is part of train, even though if I execute the same line of code for 100 times, one will be assigned for train only. One cannot be part of test. That is the purpose of random state. And 42, the reason why we take 42 is statisticians have identified that a theory behind number 42. Okay. So that doesn't mean you should always go with 42. No, you can take any integer value, 0, 1, 2, 3, so on. But they have observed that when random state is 42, the splitting is done very perfectly. The records are split in a different fashion. That is why we take 42. Okay. Next to random state, we have stratify. So the y values should also be divided because under the y, we have classes zeros and ones. Zeros and ones. So these zeros and ones have to be divided between train and test equally. That is what stratify is equals to y mean. And this data, this train test split will give us the data into actually train and test. Under train you'll have x and y. Under test also you have x and y. What is train x? Train inputs. What is train y? Under train data we have output. Test output and under test data we have inputs. That is what train x, train y and test x, test y means. So that is what you see here. I hope it is making sense. So let me execute these two lines of code together. Done. So immediately there are two data frames and two series objects. Two data frames and two series objects. test inputs, train inputs, test output, train output. I hope it is making sense. Now, I'm using SMOT. What is the purpose of SMOT? SMOT actually handles the imbalanced data. It is a technique in which the imbalanced data gets converted to balanced data. So I'm initializing SMOT. SMOT stands for synthetic minority oversampling technique. So this SMOT will be fitted on the train data. It will be fitted on the train data and it resamples the data in which it gives me the balanced data, guys. So the balanced data will be part of X train balanced and Y train balanced. Let me do it. Done. So you'll get the two objects X train balanced and Y train balanced. I'm getting the shape. So before applying SMOT, the shapes are for X train it is 3500, 11. For Y train it is 3500. After applying SMOT, the shape are, 6328, 11, 6328. So what happened? The minority class, the class with, the next number of records, they got oversampled. That is what SMOT means. Minority class, the oversampling will be done for the minority class. The synthetic samples will be created. And post completing the balancing, now the data is balanced. As we have applied SMOT, the data is balanced now. I'll use standard scalar. I'll use standard scalar. What is the purpose of standard scalar? The purpose of standard scalar is to scale the features. It uses the formula x minus mu by standard deviation, x minus mu by sigma. Right? So I have initialized, I'm using standard scalar, I'll fit it on the train data. But it is the balanced data. The X train balanced data is what I'll take. I'll fit it on the data. I'll get the transformed results. These transformed results I'm storing back to the same into a new object X train underscore scale. Now we know that this will return me a array. This will return me an array. I'll do the same on test as well, guys. Test data also I'm doing the same. So far, we have just completed the splitting part and the data pre-processing steps. Now, I'll start with, the KNN model. I'll start building the KNN model. So, I'm initializing K neighbors classifier, a function K neighbors classifier that we have imported earlier. I'm not passing K value. If I don't pass the K value, the neighbors, nearest neighbors that need to be considered, it takes the default value as 5. Okay, so let me initialize it. Done. What is the first step? We have splitted the data. Now we are supposed to train the model. We are supposed to train this model. So in order to train the model, what am I doing? I have to pass both inputs, output. If I pass both inputs and output to my model, see, this is my model, guys. This is my model in which I have stored. So I'll use it. I'll make it to train on this data, train data. So the training will be done. Yes, it is done. Post training, I'll start predicting. I'll start predicting the data. So what we are going to do here is I'll use predict function and this is my model that got trained. Yes, I'll use the model dot predict of x test because For getting the predictions, we need to pass only the inputs. We need not pass output. So I'm passing only inputs and I'm using predict function. This will predict me the predictions. And where am I storing the predictions? In an object y_test_pred. In an object y_test_pred. So let me execute this. Yes, done. Y_test_pred will be this one. So these are my predictions. These are my predictions. Only zeros and ones is what you see. Apart from zeros and ones, it will not predict anything else. So that is the example of classification. Discrete values. Predicting discrete values, fixed values. Now, let me calculate the accuracy, test accuracy. How? We have actual y, which is stored in y test. We also have predicted y. Yes, let us compare both. If you compare both, you'll get accuracy, test accuracy. Let me print this test accuracy. How much it is? 91.6%. Is that good one? Obviously. 90% is obviously good accuracy. Now, let me get the confusion matrix. Confusion matrix is one of the evaluation metric. Okay. So this will return a matrix. Depending on the number of classes that we have within the problem, confusion matrix will return a similar kind of matrix. Since I have two class problem, I am working on a two class problem, confusion matrix will return me a 2 by 2 matrix. So when I pass y actual and y prediction, this will return me a 2 by 2 matrix. See. What values are these? These are true positives, true negatives, false negatives, and false positives. Confusion matrix will return as 4 values. They are true positives, true negatives, false positives, and false negatives. Okay, so the true positives, the positive class being predicted as it is. True negatives, the negative class predicted as it is. Okay, false positives, the positive class predicted as negative class, false. And the false negatives, the negative class predicted as positive class. So these are the diagonal elements are TP and TN, and the non-diagonal elements are, the non-diagonal values are FP, FN. Okay, and always ensure that the false negatives should be very less. These are very danger. Okay, here it doesn't matter because we are working on a use case related to banking sector. But what if I work a use case related to life sciences healthcare? So in case of life sciences healthcare, the false negatives, they are accountable. We are supposed to reduce these false negatives. Then finally, I'm also getting the classification report, and this classification report we are printing. That's it. So far, we tried it only on the test data. The same steps will be applied on the train data also, guys. So this is the classification report for the test data in which we have F1 score. F1 score is nothing but the harmonic mean of precision and recall. I hope you remember the formula for harmonic mean. 2AB divided by A plus B. In the same way, it is 2 times of precision multiplied by recall divided by precision plus recall. Okay, so these are the evaluation metrics that we consider for a classification problem. Now I'll just repeat the steps that I have done for test data. I'll do the same steps on the train data. So what will I get? I'll get the, train accuracy. I'm using the model again. I'll use the model again. And this time I'll get the predictions on the train data, guys. I'll get the predictions on the train data. If I get the predictions on the train data, they are stored in an object. Where am I storing it? Y train pred. I'm storing them in Y train pred. Done. Using these predictions, I also have the actual. I'll get train accuracy. How much it is? 97%. Train accuracy is 97. Test accuracy is 92. So is that a right fit model? Obviously. It is a right fit model with a difference of 5%. It is performing well on train data as well as it is also performing well on test data, the unseen data. I'll get the confusion matrix and I'm printing the confusion matrix. So here also the performance is maintained and finally the classification report, guys. So good results with respect to both train and test data. Done. We have built an right fit model, but let us also understand the concept of hyperparameter tuning. Here, whatever the model that we have built earlier, we went with the default parameters. Like k value we have considered as 5. The value for k we considered 5. But why only 5? Why only 5 is the question. We can try with the different values of k, right? Yes. So let me take different values for k. What does a range of 3, 51, 2 returns? It returns a range object in which it stores the value starting from 3. Then the next value will be 5. The next value will be 5. The next value will be 7. So on. So all the odd numbers is what we get till 49. These odd numbers will be converted to a list object using list function. So k values from 3 to 49 we are going to take for experimenting. See, if I open k values, it will be a list object starting from 3 till 49. Making sense? Yes. Then I am coming up with 3 empty lists. One is for train accuracies, the other is for test accuracies, and the third one is for accuracy differences. The difference between the accuracies. Clear? So we are going to take all these values and I'm going to run a for loop, guys. So that let us try with the different values of k. So I'm going to start the for loop for k in k values. So k takes each value from k values from the list object starting from k is equals to 3. So that k value will be used in this line number 194. So the number of nearest neighbors that we are going to consider is 3. Number of nearest neighbors that we are considering is 3 initially. Then the model gets trained on the train data. I'll get the predictions on the train data. Next to the predictions, we are also going to get the train accuracy. This train accuracy will be appended to this train accuracies list. See, whatever we have done earlier, I'll repeat the same steps for different values of k. If I keep it in a loop, we need not run for each and every value of k. Not required. Then I'll get the test accuracy. I'll get the predictions for the test data. I'll pass both these predictions and the y actual, okay, of the test data. I'll get the test accuracy. These test accuracies will be appended to test accuracies list. So these steps, after calculating train accuracy and test accuracy, we'll get the difference calculated. How? We have train accuracy, we also have test accuracy. The difference between these two should be appended to accuracies underscore differences. What is this? This is again a list object. Right? So in this way, it helps me to get different values. I'm passing different values for k and I'm checking for the best k value. The best k value at which the model is returning us the good results. See, it tries for all the different k values from starting from 3 till k is equals to 49. It calculates train accuracies for each value of k and then the test accuracy and the difference between them. And finally, we are storing them in a list object. So it is taking time. Okay. It will complete for all the iterations for all the k values. Once after completing for all the k values, we'll make it as the data frame, guys. Let it complete. Yes. Is it done? Now, I'll come up with a data frame. So data frame is a function within the pandas. So in which I'll have 4 columns. The first column is k values, taking different values from the k. Then the second column is train accuracy, where we'll give the values from the train accuracies list. The third column is test accuracy and the fourth column is difference. The difference between accuracies. So these results, I'm converting as a data frame and the data frame object is named as results underscore df. So let me open results underscore df data frame. So this is my data frame of size 4. Now you observe carefully k value, train accuracy, test accuracy and the difference. So the k value is 3. How is the difference? 5%. 98 on train, 92 on test. The difference is 5. Accepted. K value being 5. 97 for train, 91 on test. The difference is again 5%. 5 point something. So in this way, I clearly see that as K value is increasing, what's happening to the accuracies? They are decreasing. The train accuracy is decreasing. Even the test accuracy is also decreasing. Why don't we visualize a plot on this? Right? Why don't we visualize a plot? Now let us visualize a plot on this, guys. For that, I'm coming up with a plot where I have a function figure from matplotlib.pyplot. PLT represents pyplot. Yes. So it creates me an empty figure of size 10, 6. 10 in width, 6 in height. Then the first line number 220 says that from PLT pyplot, I'm using a plot function which takes the values of k. Okay, the results underscore df is a data frame from which I am taking the values of k. Okay, then next to it, I am going to take the train accuracy. Okay, I am going to take the train accuracies and the label for it, I am keeping it as train accuracy. The label for this line plot is I am keeping it as train accuracy and markers will be kept as O's. I'll also come up with one more line plot for coming up with test accuracies. X label will be K, number of neighbors. Y label will be accuracies. And the overall title for the plot will be train and test accuracies for different K values. And I would also like to have this legend, and it should show with us a grid in the background and show function to display the plot. So I'll execute all these lines of code together. This will return me a visualization, a plot, and I can clearly understand this visualization. Focus. The overall title, Y label, X label, the legend. So the blue color line indicates train accuracies. Orange color line indicates test accuracy. Right. Now, what do we have on the x-axis? K values. Yes, different K values. On the y-axis, accuracies. So if I take K is equals to 3, if you see here, so this is my train accuracy, 98%. Test is 93. So I can clearly understand as K value increases, accuracies are also decreasing. They are decreasing. They are not increasing. So I should obviously select either K is equals to 3 or K is equals to 5. Only here the results are very good. Right? That is what I can interpret. So you have to experiment with the different values of K. If you don't experiment with the different values of K, you cannot interpret it. For this data, as K is increasing, the accuracies are decreasing. For other data, it may increase. We cannot, upfront tell that. So that is why we experiment with the different values of K. And finally, I'm performing hyperparameter tuning to get the best model. To get the best model, I'm coming up with hyperparameter tuning. So I'll define the hyperparameters in which I'm taking the K values, 5 different values. I'm taking K is equals to 3, 5, 7, 9 and 11. Okay. And the weights, on what basis the new data point has to be assigned is I take with both the distance and uniform weights. And for calculating the distance, the metric that I am going to take is Euclidean, Manhattan and Minkowski. The 3 distance formulas. So these are the different hyperparameters I am defining within a dict object. Within a dict, I have them as key value pairs. Now I'll define initialize grid search CV. I'll initialize grid search CV. What exactly is grid search CV? Grid search CV is a hyperparameter tuning technique which tries all the combinations. What do you mean by combinations? Let me talk about it. What are the different hyperparameters that we took? K, weights, metric. So when we use grid search CV, it tries all the combinations like K is equals to 3, it takes uniform weights and the metric as distance. This is one combination. Then K is equals to 3, weight is equals to uniform, metric will be Manhattan. So this will be the next combination. In this way, it tries for all the combinations within the grid. That is called grid search CV. In short, you can represent like this. Grid search CV is represented as a grid which tries all combinations. It tries all combinations. Because it tries all combinations, grid search CV is very slow. And if you are trying to do grid search CV on, if you are trying to do grid search CV on a large data set, it is computationally expensive. It takes lot of time to compute the results. So in general, grid search CV is applied on small data sets. And even when the number of hyperparameters are less in number, we go with grid search CV. There is one more technique called randomized search CV. This randomized search CV does not try all combinations. Only tries random combinations. Out of these random combinations, it gives the best results. But grid search CV tries all the combinations. Out of all these combinations, the best results will be returned. The best combination will be returned as output. Okay. So I'm initializing grid search CV, where the model that has to be taken, the estimator I'm giving as K neighbors classifier. The param grid is nothing but this param grid. Okay. The scoring that I would like to take is F1 score. Cross validation, I'll go with 5. So what exactly cross validation is? The data that we pass will be split into 5 different parts. Okay. In which 4 parts will be used as train and 1 part will be used as test. Okay. That is how cross validation helps us. And verbose to display the progress, and n underscore jobs for using all the processors. Okay, the disks within the machine. To compute this task, we are using the entire all cores, and I'm initializing my grid search CV hyperparameter tuning technique. Where am I storing it? I'm storing it under grid underscore search. Once after initializing, I'll use it on my test train data. I'll use it on my train data. I'll fit it on my train data, and this tries all the combinations. See, fitting 5 folds for each of 30. Why it is 30? Here 30 possibilities are there. So 5 into 30 are 150. 150 fits what we get. It tries all the combinations. Yes. Now, there is a attribute called best underscore params underscore, which returns the best parameters, the best combinations. Okay, so let me get this best estimator as well. Now I'm going to return the best parameters, the combination of the best parameters. What are they? K value being 5, metric is Manhattan, and the weights is distance. So this is the best combination out of all the 150 combinations that were being tried. Now I'll use this best combination to predict on my test data. I'll get the predictions. Yes, these predictions got stored to, y underscore best underscore pred underscore best. I'll calculate the accuracy score. Okay, as I have the actual and the prediction, I'll repeat the same process. But these results are related to the best combination, guys. The best combination is what we got here. It is 92% on the test data. Then the confusion metrics. Using the best parameters, these are the confusion metrics. They got reduced? Yes. And finally, I'm going to get the classification report on the test data, using the best parameters. So once if you find the best parameters, you got the best model, this model will be saved to use it on the new data. To predict the new data, we have to save it. So I'm saving this model, guys. We have imported joblib, right, initially. This joblib I am using. From joblib, there is a function called dump. There is a function called dump. I am using this dump function to save the best model. Where is this best model? Best underscore KNN is nothing but my best model. So I have it here. I want to save it in my local machine with this name. By default, this stores the weights. the model in an encrypted format, and the extension for this model you'll find it as PKL, which is called as pickle file, which is called as pickle file. So I'm storing the model. Done. Where this model gets stored, in my current working directory. At this position, in this location, it stores the current, it stores the best model with this name, and I'm just printing a message. That's it. Model got saved as best underscore KNN underscore model.pkl. If you want me to show this file, yes. If you see here, so this is my current working directory, downloads. So this is the model that got stored. If you open it, this is a pickle file. Even if you try opening it, you cannot understand it. See, it stores in an encrypted format. It's taking time. See, this is how, the results will be stored. The PKL file, .pkl. I hope it is making sense. Now, once after saving this model, we'll use this model on the new data to predict. That is how supervised algorithms help us for predictions. Help us for predictions. So any technical questions? All kind of technical questions will be answered. So if you have any questions, do post them in the chat. I'll be answering your questions, guys. And if you find the session went well, hit on the like button. It's a kind of, encouragement that you're going to provide from your side. Hit on the like button. The feedback link has been provided. Please provide your valuable feedback before you leave. And do hit on the like button.